Thank you so much for joining us for today's Protocol Labs Research Seminar. Today we have Srinath Setty from Microsoft Research presenting his work titled NOVA, Recursive Zero-Knowledge Arguments from Folding Schemes. Srinath's current projects focus on proving the correct execution of stateful and concurrent services in zero knowledge, distributed ledgers and blockchains, and unobservable communication. Srinath received his PhD in computer science from UT Austin, where he co-founded the Pepper Project. Thank you so much for joining us today, and I'm going to let you take it from here, Srinath.
Thank you all for joining, and thanks for inviting me to speak at this place. So this talk is about NOVA, which is a recursive zero-knowledge argument. This is joint work with my former MSR interns, Abhiram and Iana. I think both of them are in the call, so one of us should be able to answer any question about NOVA, so feel free to ask any question. Let me start with a simple question, which is, what is NOVA? So NOVA is a SNARK for iterative computations. For example, the prover wants to prove that Y is the output of some computation applied repeatedly on some input X. Here, F is potentially non-deterministic computation, meaning that it can take some advice or some hint from the prover at each invocation. And X is the input and Y is the output of this computation. There are many applications of such SNARKs, including VDFs, rollups, and also as a backend for Turing-complete SNARK languages such as LERC from Protocol Labs. So in the context of a VDF, this function F is going to be some delay function, meaning that it's a function that takes some non-trivial sequential computation for each invocation. Some examples include computing the Q root or fifth root inside a finite field. So in the context of a rollup, F takes as input some Merkle root of state and some transactions which are taken non-deterministically. F would execute those transactions, and the output of each step would be the updated Merkle root of the state. And in the context of LERC, F would execute a step of the program in the LERC language. So before I actually dive deep into details of NOVA, let me highlight some of the key characteristics of NOVA. Some of these might not make sense when I present, but hopefully by the end of the talk, they all make sense. So first, NOVA does not require a trusted setup. Second, it does not perform any polynomial division or multiplication, for example, through FFTs. So it works over any cycles of elliptic curves, for example, sec-P or sec-Q. It also works with FFT-friendly cycles of curves, for example, the pass the curves from Zcash. In NOVA, F is specified with Darwin Cs. Finally, I think NOVA is the simplest proof system. It provides state-of-the-art efficiency. First, the prover time is dominated in NOVA by two multi-exponentiations of size C, where C is the size of the computation at each step of the incremental computation. As I'll tell you later, we haven't fully implemented NOVA, but we expect this to provide up to 2 orders of magnitude speed up over other popular SNARKs. And this is based on the two multi-exponentiations that we need, and also another system that we built called Phalanx, which can be seen as a non-recursive version of NOVA. The size of the verifier circuit in NOVA is constant sized, and in particular, the size is dominated by two scalar multiplications. As a result of this, NOVA achieves the lowest recursion threshold in the literature. The proof sizes in NOVA are a logarithmic number of group elements, and in practice, this is going to be a few kilobytes in practice. So before I describe how NOVA works, it might be worth considering how to prove these incremental computations using some naive approach. So in the naive approach, one could just take this n iterations of F and unroll that computation into a single circuit. One can then apply some state-of-the-art SNARK to produce a proof. As you can expect, there are many downsides to this naive solution, which is, for example, the prover would require memory proportional to the size of the unrolled computation. The proof is also not incrementally updatable, meaning that if, for example, the prover has produced a proof for some n iterations, and then if it wants to produce a proof for the n+1th iteration, it has to pretty much redo the work that it did in the first place. Finally, the verifier time may also depend on n, which is, for example, if you have a SNARK where the verifier time is polylogarithmic in the size of the circuit, then it would obviously depend on n. So the notion of this incrementally verifiable computation addresses all these problems. At a very high level in incrementally verifiable computation schemes, what the prover does is it instead of proving f applied n times, it's going to proceed in incremental steps. And in each step, it's going to prove the correct execution of an augmented circuit. And this augmented circuit I've denoted with f prime here. And what this f prime does is it not only executes f, but it also proves the correct execution of some verifier circuit. So what this verifier circuit does is it actually takes a proof from the previous step and it verifies that the proof holds, or the proof is valid. As a result, if you look at the output of any step, it includes the output of the computation thus far, and then also a proof that all the prior steps have been executed correctly. So as a verifier, the verifier only needs to look at the final output of this incremental computation and also the final proof that was produced. As I mentioned, there are many approaches to build IVC. So I'm going to start with 4 different approaches. I think one of them is NOVA. So I'm going to highlight the advantages and disadvantages of the different approaches before I dig deeper into NOVA. So one could build IVC using SNARKs with trusted setup, for example, GGPR13 or Grok16. So here, it would require cycles of pairing-friendly elliptic curves. As a result, the prover will be concretely inefficient. So it also requires a trusted setup because the SNARK requires a trusted setup. Third, the prover actually must produce a SNARK at each step because the verifier circuit is going to verify that. The size of the verifier circuit is going to be determined by the cost of verifying a SNARK at each step. There are some recent works, for example, Spartan, that avoids the trusted setup. So if one builds IVC using such SNARKs without trusted setup, of course, we would avoid the trusted setup issue. With Spartan, we could also work with any cycles of elliptic curves where the discrete logarithm problem is hard. So we no longer need cycles of pairing-friendly elliptic curves. So it's going to make the prover a bit more efficient. But there are still some issues, which is the prover must still produce a SNARK at each step. And the verifier circuit must fully verify the SNARK at each step of the prover's computation. Halo addresses this last issue, which is that the verifier circuit does not fully verify a SNARK at each step. It partially verifies a SNARK, and it defers the most expensive part of verification to a later step. It also does not require a trusted setup. Unfortunately, the prover must still produce a SNARK at each step, so it still retains this limitation. And it also requires FFT-friendly cycles of elliptic curves, which can be a limitation depending on the cycles that are available. NOVA addresses all these limitations. First, it works over any cycles of elliptic curves where the discrete log problem is hard. It does not require a trusted setup. At each step of the computation, it does not produce a SNARK. Instead, the prover simply commits to some witness and some cross term, which I'm going to tell you more later. And the verifier circuit does not verify any SNARK because it was not produced in the first place. It just computes some random linear combination of the commitments. Compared to all the prior approaches, NOVA does have some limitation, which is that it requires some auxiliary proof system to compress proofs. Otherwise, the proofs are going to be large. Unfortunately, these compressed proofs are not incremental. I'll come back to this later in the talk. NOVA is also related to another approach called split accumulation. Our paper has more details about this relationship, but at a very high level, NOVA is more efficient, more direct, and also provides a native scheme for doing this proof compression. So if you zoom out a little bit from this comparison that I presented, so if you use SNARKs with or without trusted setup, the prover would produce a SNARK at each step, and the verifier circuit would verify the SNARK at each step. Halo improves this a bit, where the verifier circuit verifies only a part of the SNARK, and it defers the most expensive part of verification to later part in the computation. In contrast, Nova does not produce a SNARK at each step. The prover would just commit to some vectors, and the verifier circuit does not verify any SNARK. It just defers checking an entire R1CS instance. It not just defers polynomial evaluation proofs, it defers an entire R1CS instance. And the secret sauce for Nova is what we call a folding scheme for NP. Here, it's a protocol between a prover and a verifier, and the prover has an NP instance, for example, some R1CS instances U1 and U2, and it also has some purported witnesses W1 and W2, and the verifier simply holds the instances U1 and U2. And the goal of the verifier is to use some hint from the prover, and then it wants to output some instance U such that U is satisfiable only if and only if U1 and U2 are both satisfiable. And then another requirement is that verifying U is concretely cheaper than verifying both U1 and U2 individually using their purported witnesses. So this is inspired by the bulletproofs inner product argument, where in each round of the bulletproofs argument, both the prover and the verifier combine two n-sized inner product instances into a single n-sized instance. But unlike the bulletproofs IPA, folding scheme is defined with respect to an arbitrary NP relation, for example, R1CS. One thing that I want to point out before going further is SNARKs. If you have a SNARK for NP, it trivially implies a folding scheme for NP. Here is how that goes. The hint that the prover could provide is just a SNARK that U1 is satisfiable. And the verifier would just verify that hint and then set the folded instance to the second one. And this would trivially provide a folding scheme for any NP relation. One of the key contributions of Nova is to design a folding scheme for NP without actually relying on SNARKs. So to explain how this folding scheme works, I'm going to start with, so because we're going to use R1CS, I'm going to just recap what R1CS is. It looks like there's some question in the chat. Just to recap R1CS, there are three public M cross M matrices ABC and some public input X. The problem asks, does there exist some witness W such that this relationship holds between the three matrices? Here, this small circle is the entry-wise multiplication of vectors, and Z is the concatenation of the witness, the public input, and the scalar one. And I'm going to use this particular version of the instance where it includes not only the ABC matrices, it also includes a commitment to the witness and the public IO. In standard R1CS, there's no need for the instance to include the commitment, but I'm going to use this because we are going to rely on this later when we use it. And I'm also going to assume that these commitments are linearly homomorph. For example, I could think of them as some Peterson commitment to vectors. Before I describe how Nova designs a folding scheme for R1CS, I'm going to start with some Strawman approach. That's not going to work, but it illustrates, it actually motivates Nova's approach. So suppose P holds the two witnesses, as I set it up earlier, and suppose the verifier holds two instances. These are the commitments to the purported witnesses, as well as the public IO of the instance. And suppose in the Strawman approach, V picks a random R and sends it to the prover. And then the verifier computes the new instance, and it's going to do it as follows. It's just going to take the two commitments, and it takes a weighted sum of the commitments using this random R. And because the commitment scheme is linearly homomorphic, it can do it locally without anyone's assistance. And it's also going to take a weighted sum of the inputs to the instances. And the prover is going to also do the same thing on its side. It's going to take a weighted sum of its witness vectors. Unfortunately, this is not a folding scheme because I'm going to describe more, but the key is that the key problem is that there exists some R for which the resulting instance is actually not satisfiable, even if the original instances were satisfiable. So it does not even satisfy completeness property. So just to illustrate why it does not satisfy completeness property, let's look at these equations. So let's first start with the left-hand side, which is this AZ product with Hadamard product with BZ. And if you expand this product by substituting Z, which is the weighted sum of Z1 and Z2, we get this. And suppose we distribute this, then we collect the terms. We're going to end up with this on the left-hand side. Suppose we do the same on the right-hand side. We take CZ and substitute the value of C. We're going to end up with this. So even if AZ times BZ was CZ1 and AZ2 times BZ2 was CZ2, there exists some R for which the left-hand side and right-hand side won't match. The main reason is the left-hand side has many of these cross terms that we haven't accounted in the standard Darwin Cs. So this motivates another contribution in NOVA, which is the introduction of this new characterization of NP called relaxed Darwin Cs. So in relaxed Darwin Cs, it looks very similar to a standard Darwin Cs, except that there are two additional terms. One is this scalar U and a vector E. And the Z is also modified to include the witness, the public IO, and U. Here, the witness is going to be two vectors. One is the Darwin Cs witness W as well as the slack vector E. And the instance consists of commitment to W, commitment to E, the scalar U, and the public IO X. And in the paper, we also show that relaxed Darwin Cs and Darwin Cs are both characterizations of NP. The main reason is we can convert any Darwin Cs instance into relaxed Darwin Cs instance and vice versa. Just to illustrate this, for example, if someone has an Darwin Cs instance, they can just set U to 1 and the vector E to a vector of zeros, and they would get a relaxed Darwin Cs instance. So the folding scheme, it turns out that relaxed Darwin Cs naturally supports folding, and I'm going to just describe the protocol. Suppose as before, we have the prover with the two witnesses, and the verifier has two instances. Here, the prover starts by providing some commitment to the cross term, and this cross term is the extra terms that you would end up if you take a random linear combination of the instances. And B picks a random R and sends it to P, and then B would compute a new instance by taking the weighted sum of W commitment and then the weighted sum of the commitment to the slack vector. And it's going to use this cross term that came from the prover. It also takes the weighted sum of the input and the U term. And P does the same on its side by taking the weighted sum of its witness vectors. So in the paper, we prove that the scheme provides completeness, knowledge soundness, and zero knowledge. At a high level, the rationale for designing this relaxed Darwin Cs is that this extra term U absorbs all the cross terms, and U absorbs the multiplicative factors when you take the weighted sum of the two instances. So the key takeaway here is that by adding these extra terms, we were able to fold two relaxed Darwin Cs instances such that the resulting instance has the exact same structure. So going from this folding scheme to IVC is pretty straightforward. It's very similar to how it's done in prior works, including the ones that rely on SNARKs. So I'm going to only just provide a very high-level sketch here. So what we're going to do is we're going to represent F prime, this augmented circuit, as R1 CS. And then at each step, the way the prover would produce a proof is it would commit to the witness associated with this F prime, as well as the cross term that I showed earlier. And that's the only proof that it passes to the next step of F prime. And then the verifier circuit, it internally maintains a running relaxed Darwin Cs instance. And as soon as it sees this pi I, it would just fold those commitments into the running instance. And the running instance is also a set of commitments, and it has the same structure as a relaxed Darwin Cs instance. In iterations, the prover is left with some running instance and a witness. So to prove that it has computed this n iterations of F, what it can do is it can just send this final folded instance and the final folded witness to the verifier, who can just verify it's valid. Unfortunately, this would mean that the IVC proof sizes are of size linear in the size of the step. And there are two issues. This is large both asymptotically and concretely. And these proofs are also not zero knowledge because the prover is sending the witness in plain text. So in theory, one can prove the knowledge of a valid IBC proof using a black box use of SNARKs. And this would provide succinctness and zero knowledge because the prover holds the IBC proof and it's just sending a succinct proof that it actually knows the IBC proof. Unfortunately, this can be quite expensive because in this naive solution, the prover actually must prove certain things, such as it knows some W, such that W is a commitment to commitment to W equals this W hat, which is part of the instance, among other things. And these kind of expressing these kind of relationships could be expensive because it involves cryptographic operations represented as a circuit. So Nova's solution to address this problem is to interpret these commitments to vectors as polynomial commitments to some multilinear polynomials. So once we do this, we can actually use a variant of Spartan to directly prove that the commitments satisfy relaxed Darwin Cs without actually having to represent those polynomial commitment operations inside a circuit. By doing this, the proof sizes go down from linear in the step size to logarithmic in the step size. More recently, we also designed a variant of this approach where we directly use inner product arguments to prove that the commitment satisfies relaxed Darwin Cs relationship. This provides about a 5x reduction in proof sizes because it avoids the sum check protocol in Spartan, but it incurs slightly higher cost to the prover to produce this final proof. So before I describe the current status of NOVA and conclude, there are some limitations of NOVA, which you might have noticed already. The first is that zero knowledge is limited to the context of a single prover. But this is not really fundamental. There are other works in this space that which propose techniques to extend NOVA-like techniques to support zero knowledge in the multi-prover case. And some of those techniques also apply to NOVA. There are more fundamental limitations, which one of them is that the IBC proofs, as I mentioned, are of size linear in the size of the step. The compressed proofs are logarithmic, but they are not really incremental because if someone has a logarithmic size proof, they cannot apply additional iterations of F and produce a new proof. They really need this linear sized IBC proof to continue the incremental computation. So an open question here is designing an IBC scheme with succinct proofs while retaining other characteristics of NOVA. And I believe this remains an open question. And those other characteristics are that we want a small verifier circuit and an efficient prover. So finally, in terms of status and ongoing work here, we have a partial implementation of NOVA in Rust. It's open sourced on GitHub. The code is generic over a cryptographic group. It also implements the inner product argument based final SNARK to compress IBC proofs to get logarithmic sized final proof. And thanks to contributions from Chime and Friedel from Protocol Labs, it also supports pass the curves, and it supports R1CS expressed with Bell-Pearson's constraint APIs. So in terms of ongoing work, we are currently working on implementing a verifier circuit, so one can do recursive proof composition here. And we also are exploring other variants of NOVA to support other use cases. Finally, to summarize, NOVA is a recursive SNARK for proving incremental computations expressed with Darwin Cs. It does not require a trusted setup. It works over any cycles of elliptic curves, and it provides state-of-the-art efficiency in terms of prover time, the verifier circuit size, and in terms of final proof sizes. And with that, I conclude my talk, and I'm happy to take any questions.
Hi, Srinath. Thanks for the talk. Have you explored the possibility of proving the final polynomials using something requiring sparings and maybe KZG or something like this to get succinct verification? Or is it not possible or difficult because it's multilinear or something?
Yeah, I think we thought about it, but we don't have a full solution there. I think the difficulty there is because these commitments are going to be I guess there are maybe just stepping back, there may be, I think if you want something pairing friendly, I think it's also possible to use in the commitment scheme, we could use, for example, the G1 of the pairing-friendly curve. But then I think the issue is that we would need a cycle of pairing-friendly curves, which could make the prover concretely more expensive. But if you want to use D-log curves for the main computation and then just the pairing-friendly curves for the second, for the final SNARK, I think then somebody has to do the work of translating this D-log curve work into the pairing-friendly curve. I think that could be expensive, but I don't have a great answer there or great solution.
Okay, thanks.
Thank you so much.
All right, thank you everybody so much for coming today. Srinath, we had a great time having you. Great presentation, a lot of good questions. For anyone who would like to stay up to date on the best way to find out when we have our next seminar, please give our Twitter handle a follow @ProtoResearch. You can also send us an email at the email address of research@protocol.ai if you yourself would like to present your own research in this seminar series. So thank you again, Srinath, really appreciate it, and we hope everyone has a great day.